So number 35 is an interesting one. Consider the ballistic pendulum discussed in example 6.5 and illustrated in figure 6.12. Determine the ratio of the momentum before and after the collision to the momentum immediately before the collision. Show that the ratio of the kinetic energy immediately after the collision to the kinetic energy immediately before is given by m1 over m1 plus m2. This is a black level problem, but honestly, I think it's fairly challenging just because of the algebra involved. So first of all, we know the momentum of the bullet before it hits the pendulum is going to be m1 v1, where m1 is the mass of the bullet, v1 is the initial velocity. Afterwards, momentum must be conserved. So the momentum of this after the bullet embeds in there has to be the exact same value. But it's now moving with some velocity, which I'll call v2. So what do we know has to be true? Well, the initial momentum, which is what we have over here, has to equal the momentum of this combined thing, now moving with some velocity v2. But the mass is now the sum of the bullet and the block being m2. If you solve this, you can actually solve for v2. So ratio of the momentum before and afterwards, you could easily, for A, just show this has to be true. You could rearrange it a little bit. I did for v2. Basically, that's A. But now the more interesting part. Show that kinetic energy before and afterwards is related by this expression. So beforehand, the kinetic energy 1/2 mv squared is going to be 1/2 m1 times v1 squared. Afterwards, it gets a little bit more exciting. The mass is now the sum of the bullet and this, and the velocity, v2, is given by this whole expression, which I'm going to plug in and square down here. This gets a little bit messy, although one nice thing about it is the m1 plus m2 in the denominator squared is going to cancel out one of them with the m1 m2 in front here, and it's going to give us this expression. Looks hideous, it looks horrible. You end up with 1/2 times n1 squared v1 squared over the denominator m1 plus m2. But compare it again to this original kinetic energy. All we need to do is to factor out 1m1 out of this top and move this denominator separately, and you'll discover this is true. So we're factoring these out of that term. This is equal to the original kinetic energy, and so the final kinetic energy is just given by this term in front, which is the term you see up here. So yes, it does work, although it does require some algebraic manipulation. Good luck with this one. Hope you enjoy it.